Then renewable energy application in power converters means power electronics part. We have used in renewable energy sources. How to application, and now we have discussed with the conventional inverter. Then we have discussed with the multi-level asymmetrical inverter and its control, and some research topic we have discussed with the control hardware and future work with the renewable energy integration with the power converters. Now, now renewable energy, the forecast for the 2024 and beyond, the predict a strong growth across the multiple sector driven by the technological advancement, supportive government policy, and the global shift toward the decarbonization. So this is the importance of the forecasting help in grid management, energy trading, and integrating renewable into the grid. The key point of the uh, renewable energy forecasting ensure the grid stability, optimize the energy production, minimize the reliance on the fossil fuels. Uh, this is the introduction of the renewable energy forecastings. Uh, there are few types of the renewable energy forecasting: solar, wind, hydro, and others. Others like hydropower, battery storage, green hydrogen. These are the others. And importance of the forecasting in the integrating renewable energy into the grids. Objective of the forecasting ensuring the reliability, minimizing cost. Now we have discussed with the solar power forecasting. Basically, wind power forecasting. Then we have discussed with the solar power forecasting. Solar power is a photovoltaic capacity expected to lead renewable energy growth with the annual installation reaching record heights. New advancement in the photovoltaic cell and bifacial solar cell are the increasing efficiency and reducing the cost. And wind forecastings, the offshore wind, the experience a boom with the large scale project plan in Europe, the US, and Asia. Floating wind technology, the gaining traction in building energy generation in deeper waters. Now we have discussed with the hydro forecasting, the forecasting energy generation from the water from in reservoirs. While the traditional hydropower growth is showing due to the environmental concern, pumped storage project are the gaining interest for the grid stability. Now others like bifossil tidal, geothermal, or battery storage. Battery storage energy capacity will be rise as the lithium ion battery cost decline and alternative technology, example solid state and flow batteries mature. Green hydrogen is the another parts. Investment in the green hydrogen project are the accelerating to the support sector that are difficult to the electrify, such as heavy industries and transportation. Now we have discovered the power sector at a glance all India. This is the installation generation capacity sector wise. This is the data for 30 October 2000 31st October 2023. This is the sectors, central sectors. We have installed capacity almost this, and percentage of share 24%. A state sector, this is the installation generation capacity in megawatts, and this is the 24.8%. Private sector, this is the this capacity, and this is the share capacity. And total installation capacity 4,25,536, and share is the 100%. I think it is. Installation generation capacity fuel wise, this is the fuel wise in same dated the category. Suppose we have coal, this is the megawatt and 48.6%. Lignites, this is the capacity and 1.6%. Gas 25,038 capacity, and this is the share percentage of share 5.5. And diesel, this is the this, and total is this, and percentage of share 56.2%. This is the other hydro, wind, solar, and BM powers, wastage energy, and a small hydropower. This is the all capacity. We have total non-fossil fuels is this capacity and 43.8, and total installation capacity is 4,25,536, like 200%. It is the fossil fuel and non-fossil fuels capacity. And now all over India, the divided by the north side, we have discussed this capacity, and northeast we have discussed with the 3,050 megawatt almost, and east side 35,570 megawatts, western side almost 1,07,570 capacity, south side 76,391 megawatts capacity. This is the map we have capacity we discuss. And share of the renewable energy sources REC and total installation capacity in Indian grid at the different plant. Sixth plant, it is a 1980 to 95. Then that time capacity is 42,000. Seventh capacity is 63, and second annual plan 90 to 92. It will be increases. So every plan we have increases. This is the last plan, and this is the almost 3 lakhs 2083 capacity. Of day by day, we have increased the installation capacity of our India. This is the graph, and this is the area-wise graph we have discussed. And basically, in this topic, we have discussed with the solar photovoltaics, with the forecasting for the power converter we have uses. And what is the solar photovoltaic? You have already known the solar photovoltaic system, that energy directly into the grid energy, basically conversion devices used known as solar photovoltaic cell or the solar cell. You have already known what is the solar cell. So we have discussed this some solar plate, like this is the thin type films, and this is the monocrystalline solar cell, and this is the polycrystalline solar cell. And now we have most important topic is the how multi-level inverters support the variable renewable energy integration. So renewable energy generation forecasting using the multi-level inverters. Now for challenges in the forecasting with the multi-level inverters, so grid synchronization and real-time operation challenges. This is the another challenge, the intermittency in the renewable energy sources, and is the harmonic management and thermal issue in the inverter operation. And we have discussed with the diagram of some multi-level inverter topology, graphs showing the improved power quality, and case studies for real-world example with the images. And in this topic, basically, we have discussed with the conventional photovoltaic PV inverter and problems, and fed to the MLI inverter, and classified the multi-level inverter and modulation technique. So we know that there are two types of multi-level inverter. Two types of inverters: voltage source inverter. The inverter, it's we have providing the constant DC, and we have give the alternating AC. This type of inverter we have used the MOSFET, IGBT, BJT, GTO. So its output like alternating in natures. Same is the current source inverter. We have providing constant current in input side with using the PV panel, and output we have give the alternating in natures. So there are two types of inverter: voltage source inverter and current source inverter. In this current source inverter, we have basically used GTO, BJT like this. Now PV inverter and other classification. There are four types basically we have discussed in this section. First is the module integrated inverter. Here it is the a small size and lower power ratings and low power PV systems. Second is string inverter. The PV panel is connected in series and it is used in medium scale PV system, especially for the residential purpose. And third is the multi-steering. Multi-steering means PV is connected series or parallel both. So in this inverter, we have connected separate MPPT and DC-DC converter, and it is used in medium and large voltage scales. And now this is the central type inverter. In this inverter, we have used the PV steering along with the DC-DC converter are connected in parallel. The major drawback in this inverter is used of the single MPPT, means only single MPPT to drive in the all panels. Now we know that inverter. So we have know the basic H bridge inverter. What is H bridge inverter? H bridge is inverter only we have used 4 switches and like to H, and input have connected to the DC sources, and we have providing the DC sources and its output is fine to the alternating like AC. So here this inverter, this output VDC, this is the plus and this is the 0 and this is also the negative. So its output voltage AB, VAB plus VDC, 0 and minus VDC. So that is called 3-level inverters. And this is the some conventional multi-level inverters we have discussed later. Okay. So this is the problem of the some conventional inverter. Here we have discussed 3 inverter, no, 3-level output voltage. So this is the conventional type inverter. Okay, we have used in our day-by-day application. So in this inverter, we have find the more harmonics, more switching stages, large filter requirement, and high switching losses. And high switching losses means we have providing more than the 20 kilohertz, 30 kilohertz switching frequency. So switching losses will be more, and its output like the square wave. Here its output like the square wave. So its output filter is more size and cost is also more. More switching stresses means suppose here we have used 100 volt and all switches have blocked the 100 volt. So every switches have more blocking voltage. So it's more switching stresses, higher total harmonics means its output like a square wave. So harmonics will be more. So this inverter is this converter conventional inverter and multi-level inverter have some comparison. Means conventional inverter have produce high THD, but multi-level inverter produce low THD. More switching losses we have already discussed, but multi-level we have used the reduce the harmonics and switching losses. And multi-level inverter used in any application like high level, low level, or medium level. But conventional inverter is not used for high voltage application because every IGBT have some voltage rating like 900 volt or 1000 volt. So it is not used for the high application. But multi-level inverter, there are many IGBT connected. So we have used a high voltage application and higher switching losses in conventional inverters. And but multi-level inverter we have used 5 kilohertz switching frequency. Even we have used 1000 kilo switching frequency and fundamental switching frequency also it will be working. And higher voltage level are not produced, but multi-level inverter produce the higher voltage level. I think slide is not working properly. This is the advantage of the multi-level inverter. Reduce the voltage stresses, better harmonic profile, less filter requirement, and also multi-level inverter interfacing with the renewable energy sources of the energy and so on. And multi-level inverter, its output is like a multi-steering, like a step size. So application in multi-level day by day is the various application like industry to the multi-level range in traction in novel system, high power system we have used StateCom, facts, UPFC, active power filter also we have used, and more uses the green energy sources like photovoltaic and wind energy. We have used a multi-level inverter. Now we have discussed with the multi-level inverter is two types. First, the common source multi-level inverter. There are two types like diode clamp and flying capacitor. And another is the separate source multi-level inverter. We have used the cascaded inverter and reduced switch asymmetrical inverter and switch capacitor. There are many types of the separate source inverter types like asymmetrical multi-level inverter, T types, cross switch T types multi-level inverter. There are many types of multi-level inverter use. This is the basic conventional multi-level inverters. Here in this inverter, only diode is connected across the switches. So this type of inverter is the diode clamp multi-level inverter. This is the formula for the M level. We have generated 5, 7 like this. And capacitor clamp inverter. In this inverter, the capacitor is diode is replaced with the capacitor, and this type of inverter is called the flying capacitor inverters. And cascaded inverter means H bridge we have discussed. Two H bridge is connected, then it will be find the 5 level output. So this type of the cascading in nature, so it's called this is the 5 level H bridge inverter. And multi-level inverter, there are many modulation techniques we have used. So we discuss only few modulation techniques. There are two types of modulation technique we have used: the carrier-based sine triangle PWM techniques and space vector PWM technique. But in this slide, we have discussed with the level shifted PWM technique. And another PWM technique is phase shifted. So level shifted PWM technique have there are three types. In phase disposition means all the carrier triangular is in same phase. Opposite phase opposition disposition means two upper side is same and negative side is opposite. And phase opposition and disposition means two upper side is same and negative side is same. But here in this two is same and another is different. So every type we have used. And some other PWM technique we have used like sinusoidal PWM technique to inject the third harmonics and selective harmonics technique to use the multi-level inverter. Also, space vector PWM technique is used. And now the bipolar PWM technique, we have already known the one sinusoidal carrier compare with the one reference signal compare with the sinusoidal signal, then its output will be generate the pulses. Means reference signal is greater than carrier wave, then PWM pulses will be generated. And this is the unipolar, means two sine wave is compared with the one triangle signal, so pulses will be generated. And now H bridge inverter, we have discussed the two carrier signal and compare with the one sinusoidal signal to generate the H bridge pulses. And now level shifted PWM technique, here we have discussed. Suppose we have discussed for 5 level, so we have used n minus 5, means 4 carrier and one reference signal to generate the 5 level output. This is the type of the level shifted PWM technique for 5 level inverter. And also suppose we have generated the 7 level inverter to n minus 1 carrier is 6 carrier and one sinusoidal signal will be compared to generate the 7 level inverter. So 9 level n minus 1, so 8 carrier signal and one sinusoidal signal will be compared with the generate 9 level output of the inverter. Now we have discussed with the symmetrical and asymmetrical multi-level inverters. Means symmetrical means input have, suppose this is the cascaded inverter. So this is the 7 level inverter. Here VDC, here VDC means E, the same voltage, and another module have also same voltage, and H3 is module have also same voltage. Means each inverter module have equal voltage. So that type of inverter is called the symmetrical in nature. So here this is the 7 level inverter. Here 7 level inverter, how many switches we have used? 4, 8, 12. 12 switches and 3 sources. DC sources we use to generate the 7 level output voltage. But in this inverter, for 9 level inverter, here the equal DC link voltage we have used to generate the 9 level output voltage. Here 1 H bridge, 2 H bridge, 3 H bridge, 4 H bridge. Total 4 H bridge to generate the 9 level output voltage. But we can reduce the its switches using the unequal DC sources we have used. So here we have discussed next topic, unequal voltage. Here DC link voltage is not same in this inverter. Here suppose we have used 100 volt, so here we have used 200. So in this inverter total output voltage is 300, means 300 positive and 300 negative, and one also 0. So total we have generated the 7 level of the system. So how inverter is work? Suppose here we can flow the current like this. So this is the 7 level, and suppose here the equal DC voltage, here 100 volt, and here 3 times, it's 3 times of voltage, like 300. So same inverter will be generate the 9 level output voltage, but both inverter have unequal DC sources, but switches will be same. So this type of inverter is called the asymmetrical in natures. So here 9 level almost 8 switches we have used, and here 7 level almost 10 switches we have used. So switching will be reduced. So now we can make another type of inverter. So this is the 3-phase inverter we will discuss later. So classical multi-level with asymmetrical multi-level, some limitation is there. So classical multi-level, basically we have used the cascaded multi-level types, but new types multi-level we have designed its topology. So we have discussed the reduced switch multi-level inverters. So this is the T-type multi-level inverters. T-type means here H bridge or here another switch like a T. So here this is a bidirectional switches. The auxiliary circuit we have used the bidirectional switches, means suppose this current following for this direction and this is also this direction. Both direction current will be following. So this type of circuit for the 5-level inverter, how it is work? Suppose here VDC, So like BDC here, this is the load. So this switches S1 and S3, sorry, S1 and S5, S1 and S5, they connected the positive VDC, and again S1 and S2, two VDC, two VDC, and this is S5 and S1, one VDC. So it is two VDC and one VDC, and zero is 5 and 3. This is zero. Same is a negative like this, S4 and S1. So minus BDC, and S4 and S3 minus 2 BDC. So total output is the 5. Here we have switching table. Switch S1, S5 is on, then we can find BDC by 2. Switch S2 and S5 is on, then BDC. And this is the retardancy path for 0. There are two retardancy path here. We have discussed retardancy path. Suppose here we discuss every switches, the black lines dotted, blacks bold line have the path of switches. So this is the BDC by 2, and this is the negative BDC by 2, and this is the another BDC by 2, and this is the another positive BDC by 2. And 0 is like this, S5 and S3. This is 0, and also S4 and S2 is the 0 condition. So there are two retardancy paths here mentioned. And now this inverter, we have only connected, increase the one DC source and one bidirectional switches will be added here. One DC sources and one bidirectional switches will be added. Then it will be generate the 7 level output voltage. So, and suppose we have add the another DC sources and one bidirectional switches, then it will be generate 9 level output voltage. So it's the generalize the models. Now this section we have proposed the 7 level PV inverters. This is the proposed 7 level. This here new type of the PV inverter, and here only two DC sources will be connected. BDC1 and BDC2, and its ratio is 1:2, means here we have used the 100 volt and here is used 200 volt. So total output voltage is 300 volt. So how it is working? Like this. Suppose this is the load, we have connected two BDC like this, and this is also one BDC, and negative like this path, negative like this path, minus 2 BDC, and also negative like this path, minus 1 BDC, and this is the 0, S1 and S2 is on 0. So it will be generate the 7 level output voltage. So how many switches in this inverter? T1, T2, T3 and T4, and S1, S2 is the bidirectional switches here we have mentioned. So 6 switches to generate 7 level output voltage, but previously we have discussed for 8 switches for generate the 7 level output voltage. Means this inverter is the reduce the switches and reduce the component. So this is the asymmetrical type reduced switch multi-level inverter. So its input voltage is ratio is 1:2, and in this inverter only 2 switches will be conduct at a time. So here only 6 power electronic switches will be used, and gate driver also 6 used. The size will be reduced, and 2 DC sources BDC1 and BDC2 is used, and conduction and switching losses will be also low. Total standing voltage means every switches will be blocking voltage. So all the switches blocking voltage is called the total standing voltage. So total standing voltage will be low. So this inverter is published the IT Renewable Power Generation in 2017. This is the new type of inverter. Now this is the switching table of the inverter, means T1 and T4 is on, then it will be generate 3 BDC, means BDC1 and BDC2 will be added, and second is T1 and S2 is on, then it will be generate 2 BDC, and this is the BDC, single BDC. Okay, so there are the almost 7 positive voltage and three positive voltage and three negative voltage. So output will be seven levels. And this is the retardancy path. Retardancy path we have discussed means zero path. Suppose S1 and S2 is on, then it will find the zero path, and also T1 and T2 will be on zero path, and also T4 and T3 will be on also zero path. So there are three way to flow the current. So here we have mentioned the three retardancy path, and this is the charging where C1 and C2 is charging, we have mentioned. And now you can easily understanding for the red line when switches will be on. For 3 VDC like T1 and T4 is on, we can find the 3 VDC. When 2 VDC means T1 and S2 is on, then 2 VDC. Then VDC means we can use means 4 switch 4 and S1 is on, then like VDC is this type, and negative VDC like this type, then negative VDC, negative 2 VDC like this type, negative VDC, and negative 3 VDC like this type, means like this type, negative 3 VDC. And this is the zero. Zero means this type of zero, and another is zero. So you can easily understanding for the how to current flow for every levels. And now this is the charging and discharging for the capacitor for every levels. Here we have mentioned the level 1, level 2, level 3. Then when capacitor will be charged, here we can mention the C2 will be discharged, and here C1 will be charged. So this is the charging and discharging we have mentioned. Now this inverter will be added to switches like S3 and S4 and one DC sources. Then it will be generate the 13 level of output voltage. Means its ratio is 1 is to 2 is to 3. This is the 1, this is 2, this is 3. So its output will be generated 13 level of voltages. So this is the future of the proposed inverter, features of the proposed inverter. More output voltage stresses component will be 8, and lesser the number of DC sources are required. Lower conduction losses means this is the advantage of the inverters. And now this is the switching table when inverter will be on. This is the positive VDC, this is the positive 2 VDC, this is the positive 3 VDC, this is the positive 4 VDC, this is the positive 5 VDC, this is the positive 6 VDC. Means this is the 6 output voltage, and this is 6 negative voltage. This is positive and this is negative. So output will be 13s. Now this 7-level inverter is like a H-bridge type cascaded in nature, like to generate the N levels. Means 2 inverter will be connected, it will be generate 49 levels. Here we have mentioned 2 inverter in cascaded, then it will be generate the 49 levels. 49 levels means its ratio is 1 is to 2, 7 is to 14. So it will be generate 49 levels. So, and suppose inverter will be connected in N level. Here, I think 1 minute. Here inverter will be connected N level, then generalized form we can found in this inverter. And now the proposed inverter, we have generated we have used the level shifted PWM techniques to use the level 6 triangular and 1 sine wave compared to it. Means 7 level means 7 minus 1 carrier we have used, and 1 sinusoidal signal we have used. For 13 level means 12 carrier we have used and compare with 1 sinusoidal signal. And this is the gate pulse of the proposed inverter, and this is the hardware of the gate pulse of the proposed inverters. And now conduction and switching losses of the proposed inverter. This is the conduction losses of the proposed inverter, the conduction losses P is the any switchage of the voltage source inverter is produce its on state voltage drops and the conducting current. This is the basic formula. And switching losses, this is the basic formula. We have to find the conduction and switching losses. So conduction losses in this inverter we have used 11.21 watts and switching losses 1.3 watts. So we have used 1 kilo switching frequency. So very low power losses will be consumed in this inverter. And calculation of the total standing voltage. Here the total standing voltage VDC1 and VDC2. So this is the find out the total standing voltage of the 7-level inverter means 16 VDC, and 13-level inverter we have find the 42 VDC. This is the TSV of the proposed inverters. And now this is the blocking voltage. We have discussed now every switchage will be block some voltage. So this is the simulation result of the every switchage of the blocking voltage. So here we have mentioned T1, T2, T4, T3 like this the blocking voltage almost 20 to 40 volts. And this is the also S1 and S2 blocking voltage. This is the bidirectional switch and 160 volt. And 13 levels also we have here mentioned. And this is the blocking voltage of the every switchage of the 13 level inverters. Now comparison of the conventional inverter with the 7-level reduced switch inverter. This is the some comparison table of the like voltage stresses, switching losses, and switchage, unidirectional, bidirectional, and number of DC sources. We have comparison of the other inverter of the proposed 7-level or 13-level inverters. This is the table, and this is the capacitor C1 and C2. For this section, we use for 0.8 watt per meter square for PV. We have used the different when inverter is charging or not charging. So this is the simulation result of the 7-level inverter, and this is the experimental result of the 7-level inverter for charging of the capacitor when charge the capacitor for dynamic condition. And this is the for the 13-level inverter, the dynamic condition of the inverter simulation and experimental result. And now the proposed inverter we have discussed this is the output result of hardware experimental result of 7-level inverter, and this is the current, and this is the 13-level inverters, and this is the current. So experimental result we have here discussed. And now harmonics. Main topic is the harmonic. Multi-level inverter basically famous with the reduced harmonic. So in this inverter, only 15% is simulation harmonics we have discussed, and this is the experimentally result of harmonics we have taken from the flow analyzer, and this is the 13-level inverters harmonics, and this is the experimental of the 13-level voltage harmonics. And now this section we have discussed with the grid connected multi-level inverter with 9-level reduced switch multi-level. In this inverter, only 6 switches will be used to generate the 9-level output voltage. No any IEEE, LSBR or Science Direct will available for 6 switches for 9-level inverter. So see the inverter configuration. This inverter is only 6 switches. Here T1, T2, T3, T4, and S1 and S2. 2 switches will be bidirectional and 4 switches will be unidirectional. And its input have connected DC-DC converter and also connected to the PV panel. And inverter is connected to the grid. And here this input is also connected DC-DC converter and connected with the PV panel. Means here V upper 1 and V lower 1 is the same ratio, and V2 upper and V2 lower is the another ratio. Means its ratio V1 and V upper 1 is the 1:1, and V2 and V2 lower is 2:2. So only 2 DC sources we have used, means 1:2 to generate the 6 to generate the 9 level of output voltage. Means 6 switches and 2 DC sources will be generate the 9 level inverter. In this inverter, no any IEEE or elsewhere this type of inverter will be proposed. So this inverter is published to Journal of Circuit System and Computer in August 2019. This topology will be new for reduced switch inverter, less total standing voltage, low switching losses and conduction losses, and less driver circuit. Means switch we have used the less, than driver circuit also we have used the less, and this is the compact size and also less THD, and it is used for the renewable PV application. So this is the switching table of the proposed 9 level inverter. When switches will be on, T1 and T4 is on, then it will be added the minus VDC1, minus V2 and minus V4. So total 4 VDC. Same 3 VDC, minus 3 VDC. Another mode of 2 VDC, and this is the negative VDC. Almost 4 negative VDC, and here positive 4 negative VDC, and this is the 0. We can better understanding the power flow diagram. This is the power flow diagram of the proposed 9 level inverter. The black line will be show when inverter which switches will be on, like this. Then it will be 4 VDC, and here this 3 VDC, 2 VDC, and this is the 1 VDC, like this. Oh, sorry, this type 1 VDC, and this is the 0, and this is the negative VDC, and this is the negative 2 VDC, this is negative 3 VDC, and negative 4 VDC. Almost 9 mode of switching table we have discussed to generate the 9 level of output voltage. And in this inverter, only 2 switches will be on at a time. And this same inverter will be cascading in nature to generate the 81 level of output voltage, but its ratio will be changed. Means ratio will be how? Its ratio will be like this. Ratio is 1:1, here 1:1, here 2:2, here 7:7, and here 14:14. So it will be generate the 81 level of output voltage. And now this inverter will be connected in cascading in nature. Means inverter module like a H-bridge type. All the inverter will be connected in series. So it will be generate the generalized module, means N level inverters. And now total standing voltage in this inverter, only 20 VDC will be proposed, and this is the blocking voltage of the every switch. This is the T1, T2, T3, T4, S1, S2. S1, S2 is the bidirectional switches. T1, T2, T3 is the unidirectional switches. So this is the experimental blocking voltage of the 9 level inverter. And now this is the comparison table of the proposed 9 level inverter with the other inverter. So we can comparison with the different categories like total standing voltage, switching losses, TSB, different type of comparison table we have mentioned. And now the 9 level inverter we have use the level shifted PWM technique, means total N minus 1 carrier we have carrier signal we have used, means N minus 1 means 4 9 level, na? So N minus 1 4 carrier will be used, 4 positive and 4 is the negative. So it will be generate total 8 carrier we have used. So it's generate the 9 levels here. This is the level 1, level 2, level 3, and level 4, and also negative level 4, level 3, and level 2, and level 1. So total will be 9 levels. And this is the gate pulse 1, 1, gate pulse 2, gate pulse 3, gate pulse 4, gate pulse 5, and gate pulse 6. So here we have used the switching frequency 5 kilohertz, and this is the fundamental switching frequency for the one cycle of proposed inverter, and this is the experimental switching frequency, gate pulses. For fundamental switching frequency we have used. This is the T1, this is T2, this is T3, this is T4, this is T5, this is T6. T5, T6 means S1 and S2. Both are the bidirectional switches. And in this inverter we have 1.0 switching frequency we have used for experimentals result. This is the proposed control technique for the grid connected PV inverter, means 9-level inverter. There are two VDC sources. So this is the two MPPT controller we have used, and this is the total DC link controller, and this is the individual DC link controller, and this we can find the grid voltage, and this is the current control, and this is the grid tracker, and generate the gate pulses 6. And this is the control technique for control for the total DC link voltage. We have to control the total DC link voltage, the sum of the reference DC link voltage VDC1 plus VDC2 is the compare with the total measured DC link capacitor voltage VDC1 plus VDC2, and the output error is produced through the proportional and integral controller. And this is the control of the grid current and grid voltage tracker. Here we have discussed more how it is work, and the value of the voltage and current controller gain KP1 and KP2 and KI1 are assumed 0.97, 0.48 and 0.091 respectively. So this is for the control scheme of the proposed 9-level inverter. Here we are missing the 7-level inverter. This is 9-level inverter. And now the future features of the proposed controller. This is the control the output voltage of the solar array need to the balance the suitable synchronizing component is required so as the synchronize to the output voltage of the multi-level inverter with the grid, and the voltage level of the proposed MLI need to be maintained in all conditions. The active power need to be the transfer from the source to the grid, and the current inject to the grid should be purely sinusoidal and in a phase with the grid voltage. The current inject to the grid should be the sum of the equal to the current flowing through the MLI inverter. The grid current and inverter output voltage should be have lesser harmonics. These are the main point of the grid grid connected proposed 9-level inverters. Now this is the simulation result of the proposed 9-level inverter. Here this is the output voltage waveform, and this is the grid current waveform, and this is the experimental result of the proposed 9-level inverter, and this is the output voltage, and this is the current. And now this is the harmonics of the proposed inverter, means 1.1% harmonics of the, and this is the experimental harmonics of the proposed grid current. And now varying condition of the this is the input of the two DC sources now. So this is the capacitor wise we have used 4 capacitor. So this is the varying condition for PV irradiation, and this is the output voltage of the 9-level inverter, and this is the current, and this is the capacitor voltage. And now we have discussed 81 level inverter, means 2 9-level inverter in connected to the generate the 81 level. So 81 level inverter means its output near to the sinusoidal. We have so the zoom part of this section. So this is the level wise, and this is the output voltage harmonics, means harmonics will be very less, 1.61%. So output filter requirement is very less. And now we have discussed with the modified 31 level inverter. In this inverter, the 10 switches to generate 31 level inverter. Let's we discuss in next slide. Now this is the proposed 31 level inverter with the grid tied PV system. In this inverter, 10 switches we have used, means T1, T2, T3, T4, T5, T6, T7, T8, and two bidirectional switches, S1 and S2. We have discussed in previously how the bidirectional switches we have used, means one switches for anti-parallel diode we have used, and also we have used two IGBT connected in anti-parallel, then we can make the bidirectional type of switches. So in this inverter, two sources here. This is the one source PV1. This is the PV2, and this is the capacitor we have connected to balance the automatic balance the voltages, and also here the capacitor we have used to automatic the balance the voltage. So here one sources, here one another sources, and PV0 is used another sources. So how many sources will be used? Three sources: PV1, PV2, PV0. So its voltage ratio like this type 1:2:4.5, and capacitor voltage we have, so the voltage ratio is 1:1, 2:2, and 9. So this type of inverter will connect it the grid tied system. You have used the transformer 1:1. So in this inverter we have generated 31 level of output voltage. Only 10 switches, means 8 switches is unidirectional and 2 is the bidirectional to generate the 31 level. So in this inverter, some key points: it have reduced the number of power electronics component and switches and gate pulses. The DC link voltage are few as well as fully utilized, means all switches we have used the fully, and the total standing voltage will be proposed is less, and lower switching losses and conduction losses, means switches will be used low, then losses will be also less, and compact size means size will be also less. Easily configuration means reconfiguration type of inverter, means switch will be reconfigured, and lower THD, and 4 switches operate at a time, means in this inverter 4 switches will be on at a time. So now this is the switching state of the proposed inverter. So this is the positive mode 1 for positive VDC, and this is the mode 32 is the negative VDC. So positive 15 VDC to 0 is the positive part, and 0 to here negative 1 to minus 15 is the negative part. So total output voltage is 31. So every switches will be on, every mode will be on. So how many switches will be on? 4 switches here: T1 on, T4, T5, and T8. So it's adding the DC link voltage to generate 15 voltage. Same mode 2, adding the DC link voltage to generate 14 levels. So here we can add and subtract the DC link voltage to generate the levels. So its level is positive 15 to negative 15, means 31 levels. 15, 15, 30, and also 0 is 1 level, is 31 levels. So this inverter is also in cascading in nature. So suppose we have cascading 2 inverter, only 2 inverter. So how many levels will we generate? It will be almost 927 level, 931 levels, like this. 2 model will be add to 900 above level will be generated. So this inverter is cascading in nature, mean generalized form we have found. So this is the formula of the generalized form of proposed 31 level inverter, and this is the switches, number of unidirectional switches we have used for n level, for number of bidirectional switches used for n level, gate driver circuit for n level, DC voltage sources for n level, number of voltage level for n level. So every level we can find this formula to how many switches and driver circuit, switches, gate drive circuit, anything we have used for the proposed inverter. And now this is the blocking voltage of the every switches. This is the simulation of result of the blocking voltage, and this is the experimental result of the blocking voltage. So this is every switches. Suppose this is the VS2, and this is the blocking voltage. This is VS1 is the blocking voltage. So like T1, T2, T3, T4, T5, T6, T7, T8, S1, S2, all blocking voltage. So total standing voltage will be 64. Means output voltage 31 and its blocking voltage is 64. And this is the gate pulses for simulation result of 31 level inverters. And this is the experimental gate pulses of the 31 level using 100 hertz, 1000 hertz. Okay. And now this is the controller for the 31 level inverter. We use three DC sources. So three controller individually we have used total. And this is the current controller and this is grid tracker. And this is the gate pulses. And now filter circuit we have used. So this is the filter designing of the proposed inverters. LC, LCL types, any types filter we have used, but basically LCL filter in this inverter we have used. And now the varying condition of the proposed inverter for 1 kilowatt per meter square, 0.8 kilowatt per meter square, and 0.6 kilowatt meter per square. Every condition we have, dynamic condition we have discussed, and this is the capacitor voltage we have discussed. And now experimental capacitor voltage we have discussed. Here the capacitor voltage we have mentioned in right side. And now harmonics of the proposed inverter to grid tied system, like almost 0.8% the harmonics. And this is the experimental harmonics using the Fluke analyzer, 434 power analyzer we have used. And now this is the simulation result of the proposed inverter, and this is the experimental result of the proposed inverter. This is the grid voltage, and this is the grid current, and this is the inverter output voltage. And now hardware design implementation of the system. Suppose we have designing the PV panel. So how many PV panel we have selected? So basically here we have discussed the rating of the proposed inverter for 7 level and 13 level inverter. Here we have mentioned, and this is the solar panel we have used. So Titan ECO30H156 polycrystalline solar cell we have used, and this is the Titan 301H156 multicrystalline solar cell we have used. So in this inverter we have used. And now this is the 9 level. This is the 9 level inverter, how the PV panel will be connected, and this is the 31 level inverter, how the PV panel will be connected. We have mentioned, and this is the parameter of the proposed 9 level inverters. Every parameter we have mentioned. And now this is the circuit of the 31 level inverter. Here we have 10 switches, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is the bidirectional switches. Here we have mentioned bidirectional switches means one diode and two diode we have used to make the bidirectional switches. And this is the gate driver circuit. This part is the gate driver TLP250 based gate driver circuit, and this is the switches TLP250. This is the switches CT60M. Here we have mentioned. This is the inverter circuit, and this is the heatsink. And here we have mentioned every switches we have mentioned. And now driver circuit. How the design the driver circuit means how many types of driver circuit. Basically, there are basic 3 types of driver circuit: push-pull driver circuit. Here the graph we have showing, and isolation driver circuit. In this circuit, the TLP based driver circuit we have used, and this is the totem pole driver circuit. Now the market, industrial market, we have used the totem pole driver circuit as well as isolation driver circuit used for research purpose. So there are this is the IRF21CIC. In this driver circuit we have used push-pull, and isolation based driver circuit TLP250 based driver circuit we have used, and here the totem pole driver circuit. This is the basic circuit diagram. And design of the IGBT driver circuit this is the isolation driver circuit basic structure, and this is the physical of the driver circuit, this part, and this is the IGBT, and this is the rating of the every component, and this is the TLP 250. Now this is the isolation power supply, means driver circuit have required the power circuit plus 20 volt. So this is the circuit of the driver power supply, and this is the complete power supply. For every switch we have provided here, the circuit we have used to HB like bridge types diode we have used. And now design of the deadband circuit. Deadband, this is the basic parts of designing of the deadband parts. And now designing of the DC-DC converter, the basic formula to design the inductor, and this is the capacitor, the basic formula. And now main part is the generating the pulses. So this is the digital control DS110 DS space. So this is the circuit of the DS space. So we can generate the pulses through real-time controller like DS space. And this is the basic laboratory setup. Here the laboratory setup. This is the control part, and this is inverter, and this is the gate driver circuit, and this is the DC link capacitor, and this is the boost converter, and this is the PV panel, and this is the complete hardware setup of the proposed inverters. And conclusion, future works, reference. Thank you. So sir, I'm taking more times.
Sir, completed, sir.
Uh, Sir, almost completed. Actually, there are many parts we have discussed, but this is not a research type of program. No? So basically, we skip this part.
Okay, sir, no problem. You can discuss another.
Hmm. So, any questions regarding of designing the converter like? So, please ask me. Hello, Anil sir.
Sir.
हाँ sir. Any questions, sir?
Session up to 9.
So I have show some research parts, basically the converters. So this is the seven level inverter we have discussed in this slide. So we can make in this inverter to higher level. How? So suppose this is seven level inverter. We can add the another half here, the half part now. So half part we have used and make a half part use and so its ratio we have a seven level inverter is a 1:2 and this is suppose auxiliary circuit. Its ratio we have used the 7 time of DC sources. 1 minute, sir. Oh, okay, fine. So here is the seven. Its type is the seven level, 7 times. So it's generate the 21 level inverters. Means we can use one module for 7 level and another module we have used to generate the 21 level output voltage. So we can make a different type of inverter to connect it in. We can add the another inverter to generate the different level. This is the always only advantage in multi-level asymmetrical inverter and conventional inverter. This type of advantage is not available. So this is the 21 level inverter. For proposed inverter can be generated 21 levels using the 3 bidirectional and 6 unidirectional switches. Means this is the bidirectional switches S1, S2, S3, S4, S5, S7, S8, and S5, S6, S9 is the unidirectional switches. So, and its DC link voltage is VDC1, VDC2, this is the another VDC3 and VDC4. So total 4 VDC we have used to generate the 21 level inverter. This is the another type of inverter. So this is the switching table of the proposed 21 level inverters. To generate 21 level inverter for mode 1 positive 10 VDC, mode 2 negative 9 VDC, mode 3rd 8 VDC, mode 4 7 VDC, mode 6 5 6 VDC, mode 7 5 VDC, and another mode is 4 VDC, another mode is 3 VDC, another mode is 2 VDC, another mode is 1 VDC, and 2 mode is the retardancy path. Same is the negative VDC, negative 2 VDC, negative 3 VDC, negative 4 VDC, negative 5 VDC, negative 6 VDC, negative 7 VDC, negative 8 VDC, negative 9 VDC, and negative 10 VDC. So it is the output voltage for every level of 21 level inverter. And now this is the simulation result of the proposed inverter, and this is the current, and this is the experimental result of the proposed 21 level inverter, and this is the current. And now this is the experimental setup for hardware setup of the 21 level inverter. Now I can show some other inverter. For 21 level types. Here one inverter is the 21 level. I can show the paper. Okay, which This inverter, this inverter is recently published. This journal, believe. So you can show the configuration here. Same inverter I have discussed. So you can show the details of the proposed inverter. This inverter we can publish a conferences, but in this inverter we can publish a journal for using the renewable energy sources. So here we can details of the proposed inverter. Here the voltage ratio V1 and V2, its voltage ratio is 1:2, but here the voltage ratio V0 means here we can use only one DC source, means one DC sources will be switched by the capacitor, means this type of this is not a called switch capacitor, but DC sources will be used switch through the capacitor. So it will be auto balance. Okay, so we can use the three DC sources, PV1, PV2, and PV3. And here the DC-DC boost converter we have used, and another DC-DC boost converter, another DC-DC converter. And here the bidirectional switches, the two switches will be connected in anti-parallel, we have discussed. And this is the three level, this inverter will be produce the three level output, and this inverter will be produce 7 level output. Both is the combined to generate 21 level inverter, means 10 positive and 10 negative, and also 0. So this is the this is the this inverter will be generate 51 VDC, means this the total standing voltage is 51 VDC. And this inverter is the comparison with the comparison table, which level to switch ratio. Here the every level, this is the positive with the positive level, 9 is the also positive levels. So this is the positive parts and this is the negative parts. And this is the switches to T1 will be produce 3 VDC, T2 will be produce also 3 VDC, and T3 will be also produce 3 VDC. T4 it will be produce VDC. So we have mentioned every color we have mentioned. Means T4 will be produce VDC. So here VDC here we have discussed. S2 will be produce 2 VDC. So also here S2 will be discussed. S3 will be produce 7 VDC. So here S3 will be discussed. So every level will be produced. So I am mentioning the graph for every levels. This graphically representation. And now this is the switching tables of the proposed inverter. When switches will be on, here we can mention the switch will be on, and cross sign will be mentioned the switch will be off. So every section we have mentioned, and this is the mode 11, 12, and 13 to retardancy path, and this is the negative path. And now power flow diagram for every inverters. Means the 31 level inverter. This is the power flow diagrams. Now another types of inverter we have discussed here. For same level, we have discussed another type of inverter, 21 level. Same inverter, auxiliary circuit we have used, connected the PV sources 1 and PV sources 2. And another H bridge we have connected. This is the H bridge. You can show the details here. This is H bridge, not another inverter. But in this inverter, DC link sources put the between the switches. Okay, so this is the 3 level produce, and this is the 7 level output voltage produce. So this is the another type of inverters. So both inverter is connected in series to generate the 21 level of output voltage. So this is the switching table of the proposed inverter, and this is the power flow diagram. Red line we can show the how the inverter works. This mode number 10 means T3, T2, T6, T7 will be produce 10 VDC, and S1, T2, T6, T7 will be produced 9 VDC, and mode 3, T3, S2, T6, T7 will be produced 8 VDC, and mode 7, S1, S2, T6, T7 means like this, produce 7 VDC, and 6 VDC we can S1, as T4, T6 and T7 will be produce 6 VDC, and mode 6 5 VDC. How? T1, S2, T6 and T7 will be generate the 7 VDC. 4 VDC, T1, T4, T6, T7 to generate the 4 VDC, T3, T2, T6, T8 generate the 3 VDC, S1, T2, T6, T8 generate the 2 VDC, and this is the VDC. VDC means T3, S2, T6, T8 generate the VDC, and this is the zero level means here no any VDC will be covered. Voltage source will be included, and this is the another path for the zero VDC. So this is the another graphically representation, and this is the also, and this is the complete set of the proposed inverter. So here you can see this is the D space, and this is the PC personal computer is connected with the D space. D space will be generate the gate pulses through the deadband circuit we have used, and deadband circuit provided the pulses through the proposed inverter, and input have the inverter have connected the power supply, programmable power supply, and for measurement purpose we have used the fluke analyzer, and this is for the hardware experimental figures how the inverter will be connected. This part is the D space, this part is the inverter, this part is load. So this is the output of the 21 level inverters, and this is the experimental result of harmonics of the 21 level inverters. So this paper will be published to the Willy and comparison tables.
Thank you, sir.
Now, Anil sir, we have proposed more inverters.
Sir, thank you, sir. Thank you, sir.
Okay. Anyone ask any question regarding multi-level inverters?
Any questions?
I think no one interested.
Okay, sir. Everything you understand. I think, sir. Thank you, sir. Thank you for your deep explanation about renewable energy sources generation for at different levels of inverter used in that systems, and also inverters and converters operate at different levels.
Yes, and how to use the PV application, renewable energy sources for different level.
Different levels. How to from solar to and load centers, solar generation to AC load. In between that, inverter operations are is a how to utilize the inverter, and what type of levels are is used in that inverter circuit. So I thank you, sir. Thank you for your deep explanation of all levels of inverter circuits.
Okay,
and
thank you, sir.
Thank you, one and all. So please leave the session.